This video is brought to you by IXL, used by millions of students worldwide to get ahead in math, English, and more.
Today we'll practice approximating the area under a curve. Let's learn how. You can probably find the area under a curve like this, or even this, by using some combination of rectangles and triangles. But what if our curve looks like this? We can still use rectangles, but because our function is curved and our rectangles are not, it will be an approximation of the area under the curve, rather than an exact calculation. However, to minimize the difference between our estimate and the actual area, we can use more rectangles with smaller widths. In general, for a function defined on an interval a to b, you can approximate the area between the function and the x-axis by dividing it into rectangles whose areas equal width times height. To find the width of each rectangle, partition the entire interval into n equal subintervals. To find the height of each rectangle, we'll find where the rectangle touches the graph, so that the height will be f of xi for some x value. But how do we know which x value to use? Well, two common methods are to draw our rectangles so that the left edge of each rectangle touches the curve, or so that the right edge of each rectangle touches the curve. Adding all those rectangular areas together will give you an approximation of the area under the curve, keeping in mind that it may be an over or underestimate of the exact area. Let's practice with some examples. Estimate the area between the graph of f of x equals negative 1/2 x squared plus 7 and the x-axis on the interval from negative 2 to 3. Use 5 rectangles of equal width and write endpoints to find R5. Let's start by dividing the entire interval from negative 2 to 3 into 5 equal subintervals. To find the width of each subinterval, find the difference between 3 and negative 2 and divide by 5. So each of our rectangles has a width of 1, making our subintervals negative 2 to negative 1, negative 1 to 0, 0 to 1, 1 to 2, and 2 to 3. Because we were told to use right endpoints, we'll focus on the rightmost x value of each subinterval, negative 1, 0, 1, 2, and 3. So the overall area will be the sum of the areas of all 5 rectangles, which are calculated by multiplying height times width. The height of each rectangle is the value of the function at the right endpoint. And since the widths are all 1, we can simplify our expression to just the heights of our rectangles. We can evaluate the function by substituting the x value into the equation, or by finding the height of the graph. For example, f of negative 1 is negative 1/2 plus 7, or 13/2. F of 0 is 7, and the remaining heights are 13/2, 5, and 5/2. Adding all these terms together, the estimated area is 27.5. So how close is our estimation to the actual area under the curve? Well, over here on this interval where the function is increasing, we're overcounting area. But we're also missing all of this area over here on this interval where the function is decreasing. Since it looks like we're missing more area than we're overcounting, this is likely an underestimation of the actual area under the curve. This time, we are estimating the area of a trigonometric function using 4 rectangles and left endpoints. Given that our interval is from 0 to 2 pi, we can find the length of one subinterval by dividing the entire interval into 4 equal parts, so each rectangle will have a width of pi over 2. So our 4 subintervals are 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. Remember that we were asked to use the left endpoints of each of those intervals. To find the estimated area under the curve, we'll evaluate the function at each of those left endpoints and multiply by the width of the subintervals to find the area of each rectangle, and then add them all together. Notice how every term in this series includes the interval width of pi over 2. Let's factor that out. Now we can find the heights of the rectangles, which we can easily see on our graph are 5, 3, 1, and 3. These are also the values we'd get from plugging those x's into our function. Adding them together, we get 12 as the sum of all the heights. So our final answer is 6 pi. Does that seem right to you? Well, when the function is decreasing from 0 to pi, we overestimate the area. On the other hand, when the function is increasing from pi to 2 pi, we underestimate the area by an equal amount. So it turns out that this approximation is actually spot on. Let's try one more together. How would you approximate the area between the natural log of 6x and the x-axis from 1 to 3? Because we are using 4 rectangles of equal width, the width of each rectangle will be 1/2. Starting at 1, let's take 4 steps of 1/2 to define our 4 subintervals. Which value in each subinterval should we use to calculate the value of the function? Since the question asks for left endpoints, we'll use 1, 3/2, 2, and 5/2. Let's calculate the estimated area by adding together the areas of our 4 rectangles, found by multiplying height by width. Since all 4 rectangles have the same width of 1/2, we can factor out 1/2 from each term. To find the height of each rectangle, we need to substitute the x value into the equation ln of 6x. So our 4 heights are ln of 6, ln of 9, ln of 12, and ln of 15. This comes out to approximately 4.59. How do you think this compares to the actual area? Because f of x is increasing on this interval, and we use the left endpoints for our estimation, we repeatedly underestimated the actual area under the curve. Note that if we would have used the right endpoints of each subinterval instead, we would have gotten an overestimate. In general, whether you get an over or under approximation depends on whether the function is increasing or decreasing on that interval and whether you use left or right endpoints. If the function is increasing on the given interval, left endpoints will underestimate the area and right endpoints will overestimate it. If the function is decreasing on the given interval, the reverse is true. Great work today. Keep practicing and improving your skills.
Head over to IXL.com for more practice on this skill and thousands more videos in math and language arts.